the live board. Yeah, that's so that means I will send you a screenshot of this. The entry in the ith row and jth row, jth column. It should be column, not row. Column of G plus H is G plus H. Okay, then G sub ij plus H sub ij. I'll send you a screenshot so you can see. So we have that one. We already have that one by recalling the definition of matrix addition. And then the next one is we use commutative commutativity of real numbers or complex numbers. So from there, we know from the from arithmetic that for any two numbers, a sub ij with components ij, b with components ij is just equal to b sub j, a with components ij. And then we apply these two matrices. Apply two matrices. You have to write words because this is to prove. Okay, so each entry, oh no, it should be H, G and H, sorry. Should be G and H because we are to prove G and H. Matrices G and H should be G, H, G, H. So A plus B, entry of, I meant G plus H equals the corresponding entry H plus G. So A plus B component A. Oh, it's gone. Did you delete? It's there. Okay. I was scared because I forgot to take a screenshot of it. And then it was gone. Oh my. And then this one. So A with components ij plus B with components ij. And then that is just equal to B with components ij plus A with components ij. So this is just B plus A with components ij. So this is true for every ij. This is true for every components ij. The two matrices are equal. Are equal. I will send you a screenshot of this. It is yeah, that's A sub ij. Yeah, make sure you copy it correctly. For B, you prove that matrix addition is associative. So we're given here, you prove that G plus H plus J is equal to G plus H plus J for any three matrices. So we're given here three matrices G, H, and J of the same size. You have to have, so we write the matrices entry form. So let's say G with components G sub ij, and then for H sub ij, and then for J sub ij. And then we recall the definition of addition. So matrix addition, so G plus H sub ij, so that is the components G I sub j plus H I sub ij. All right, and then we compute G plus H plus J. Let's compute H plus J first. So H plus J sub ij is just equal to H, small h, sub ij plus J sub ij, and then we add G. So add G, so that is G plus H plus J. I hope this is not confusing for you. Equals G I sub ij plus H it's the components, because this is a matrix. All right, good, because it's taking time. All right, then we compute G plus H plus, let me delete this. We compute G, we already did that, right? G plus H plus J sub ij. Then you compute the other one, the right side. So that is G plus H plus J, the other side. So G plus H, given the component G plus H I sub ij. So this is G sub ij plus H sub ij. And now we add J. So that is G plus H plus J sub ij. This is equal to G sub ij plus H sub ij plus J sub ij. And then we apply associativity of numbers from ordinary arithmetic. Then addition of numbers is associative, so we plug in everything here. So that is G sub ij plus H sub ij plus J sub ij equals G sub ij plus H plus J. Right? Okay. Since and then you will conclude here. Since the ij entries or components of G plus H plus J and G plus H plus J are equal for all. I will just write the whole words for all instead of symbols. For all ij, the matrices are equal. No more space. Your conclusion is, since the ij entries of G plus H plus J and G plus H plus J are equal for all ij, then the matrices are equal. Then you can conclude with this one. So that's how you prove that the matrix addition is associative given matrices G, H, and J. You got it? Okay, you want to try the zero matrix? G plus Z equals G. Okay, try. You want to try it? And then I'll check whether it's correct. Okay, try it. But you only use letters because you're only given letters here, or matrices. You're not given the values of matrices. But you use the letters that is provided here. You don't use other letters or matrices. Are you writing in yellow color? Yes, I can see it. I can see it, but you have G sub. Yeah, you don't have a pen? Ah, you're using your phone. So you can save space. Okay. You define your G first from a M by N matrix and your zero matrix. Okay, that one is correct. You need to prove that this one, matrix G plus a zero matrix, is equal to matrix G. Okay. Yeah, why don't you write it on the paper and then take us a photo of it and send it to me. Yeah. All right. This is what you wrote, okay? You wrote G. Yeah, that one is all right. G is, yeah, I already got it. So Z is equal to, this is what you wrote on in the paper. So Z, yeah, and you said G plus Z equals, this is what you wrote. So I'm just trying to yeah, but you didn't this is correct. This is actually correct, but you didn't define your zero identity. You should define. You should do like this, because you need to prove that the zero matrix is an additive identity. G plus Z equals G. So you need to define that Z is equal to 0. You forgot that. Yeah. So that's Z I sub j equals 0 for all I components I j. That one. Okay. But you did it correctly. And then, okay, this one is correct, but you have to do like this. G, this one I will put here in green. G plus G sub ij, like that. Can you see that? Can you see on the live board? So G plus Z sub ij. Then you do like this. Plus 0, because you've already defined here that Z, this one. Huh? Actually, it's you define that G is matrix G is equal to its component G sub ij and matrix 0 Z sub ij, and it should be equal to 0. You have to define it. And use matrix Z sub ij is equal to 0 for all I and j components. You did it correctly, but you need to show it that it's 0. This one. You start here, this one. You need to define that 0. So you do like this. G plus ES plus 0. So this is just equal to G sub I J. Yeah? And then you can conclude that G plus Z is equal to G. So the 0 matrix Z is the additive identity for matrix addition. You got that? Eigenvalues and eigenvectors. Okay. Yeah, I remember from one of your homework, you were asked to find the eigenvalues and normalized eigenvectors. So the eigenvalue is denoted as, can you see my writings on the live board? So the eigenvalue is denoted by lambda, and the eigenvector is denoted as this one, V, bold V, or V with an arrow on top of it. So you cannot get the normalized eigenvector without finding the eigenvector first. Okay, let's say from your homework, you're given this matrix with components 1, 0, 1, 0, 0, negative 1. You were given that one from your homework. From homework. So you need to write this in it's a polynomial equation in eigenvalue or characteristic polynomial characteristic equation. So we can write this as, okay, the matrix, we use Z here. So the matrix Z times the eigenvector is equal to lambda, the eigenvalue, times the eigenvector, where the eigenvector here is not equal to 0. Can you see my writings? So you can use this characteristic equation or polynomial equation. Okay. Z is for the matrix, but you can use other matrices. Okay, Z minus lambda times the identity matrix. You asked me last time what's the use of the identity matrix, because it has 0 and only 1 value. It's useful here. Okay, and then your eigenvector, provided that your eigenvector is not equal to 0, and you need to find the determinant. So you need to find the determinant of Z minus lambda times the identity equals 0. Okay, and this one gives the polynomial equation in eigenvalue, which is called the characteristic polynomial. Do you get it? Oh, I wish the internet is very fast. Can you hear me well? Nick, hello? Okay. Oh, mathematically or what's that? Mathematically or like definition? Words? You can just say eigenvalue is a scalar value. Like say for example, it's a scalar. But vector, eigenvector has is a vector. Like say for example, for a square matrix A, an eigenvector, you can just say a scale eigenvalue is the scalar. And no, you need to find the eigenvalue first, determinant of that, before you can get the eigenvector. You solve matrix minus the eigenvalue times the identity matrix. That's how you will find the eigenvalue. Okay, I was trying to show you how to find it using an example from your homework, given the matrix 1, 0, 0, negative 1. That is the magnitude. Just the magnitude. Determinant is what we discussed last time, right? I'll show you a different example in finding the eigenvalues and eigenvectors. Because I cannot give you like more definition in words for eigen values and eigenvectors. I can only tell you eigenvalue is a scalar. And then eigenvector has a magnitude and direction. Yeah, eigenvector has magnitude and direction, but the direction doesn't change. Only the length. It doesn't change. It has a direction, but it doesn't change the direction. It's constant. Like say for example, on the x-axis, so the vector will just go constantly, but the magnitude or the length, it changes. But eigenvalue, that one is a scalar number. Multiplication. Yeah, there are two ways. Yeah, there are two ways to multiply vectors, right? That product, or what we call the scalar product, and the other one is cross product. I haven't discussed that with you yet. If you know all of those, if you know all the operations for matrices, how to multiply vectors, then you will know how to find eigenvalues and eigenvectors. So which one would you want to start? I think it's better for you to know how to multiply vectors first. And you must, why do you keep on mentioning vector transformation? How to find, okay? So let's say, let me show you before I let you go. Can you see something on the live board? So this is to calculate the eigenvalue. Let me just show you. So to calculate the eigenvalue, you get the determinant of matrix A minus, okay, the eigenvalue times the identity. So you get the determinant of matrix A minus lambda. Identity matrix is only 1, 0, 0, 0, 1, 0, 0, 0, 1. So it doesn't affect anything. So you get the determinant of this. 2 minus lambda, 1, 2 minus lambda. Okay? And then to find the determinant, this is 2 minus lambda times 2 minus lambda minus 1 times 1. So that is 1. So this is lambda squared minus 4 lambda plus 3. And then you equate this to 0. Yeah, because this should be determinant of the matrix minus lambda times identity matrix is equal to 0. So equate lambda squared minus 4 lambda plus 3 equals 0. And then you factor this. So lambda minus 3 lambda minus 1, right? Then so lambda 1 is equal to 3. You solve this algebraically. You equate each of the factors to 0. Then lambda, the other lambda is equal to 1. Then these are the values, the eigenvalues. Okay? These are the eigenvalues. And now we find the eigenvectors. So for lambda 1 equals 3. You find the eigenvectors here. So the vector A, this one, this is the formula. And then your matrix there. So you have 2 minus 3. It should be 2 minus 3 because that is lambda 1, 1, 1. And then 2 minus 3. Yeah, it's the same. 2 minus 3. It's negative 1. So this is, and then times the vector, I forgot. Then that is equal to 0. So this is just negative 1, 1, 1, negative 1. Then the vector equals 0. So that is the eigenvector. Eigenvector of eigenvalue 3. But for eigenvalue 1, lambda 2, we get the eigenvector for that. So I'm just showing you how to get it. Okay? Equals 0. Therefore, in this matrix, the eigenvalues are 3 and 1, and eigenvectors are 1, 1 and 1, negative 1 respectively. So that's how to solve it.